Hi, today we are going to talk about how to calculate amounts of products and reactants using grams. Just for a quick review, if you'll remember, we've been talking about mole-to-mole ratios, and in this example above here, if we start with, say, 1 mole of propane, we know that we will get 3 moles of carbon dioxide. Or, for example, if we would like to get 8 moles of water produced in the reaction, we'll know that we will need to start with 2 moles of propane. We'll double the number of moles of water and double the number of moles of propane. So now let's move on to calculations with grams. Here's an example for us. We're going to use the same chemical equation that's been balanced, and we're asked how many grams of oxygen are required to react exactly with 44.1 grams of propane. And here I've drawn a little plan to sort of help us. We know is what we start with what we know, and that's 44.1 grams of propane. First, what we want to do with that is we want to convert that into moles. So that'll be our first step, the number of moles of propane, finding that. Once we know the number of moles of propane, we can then determine the mole-to-mole ratio between propane and oxygen. So we'll convert, basically our equation, our formulas will convert us to the number of moles of oxygen. And once we find the number of moles of oxygen that are needed in this reaction, we can then convert into the number of grams of oxygen. So let's start with what we know. And let's take the first step in converting grams of propane into moles of propane. And if you'll remember, we'll use dimensional analysis to do that. We start with 44.1 grams of propane, and we multiply by the conversion factor 44.09 grams of propane in 1 mole of propane. And our grams of propane cancel out, and in the end, we end up with 1.00 moles of propane. So now, that's where we are right here on our plan. We need to use the mole-to-mole ratio and determine how many moles of oxygen are needed. So let's do that. We know that we have 1.00 moles of propane now, and here is our mole-to-mole ratio, 5 moles of oxygen per every 1 mole of propane. And when we multiply that out using dimensional analysis, we get 5.00 moles of oxygen. So our next step, and very last step, is converting this 5 moles of oxygen into grams of oxygen. And again, we'll use dimensional analysis. We know there are 32 grams of oxygen in every mole of oxygen. And when we multiply this out, we get 160 grams of oxygen. And that's our final answer. That's how many grams of oxygen are needed to react completely with 44.1 grams of propane in our equation. So if we do this in a more simple way, we can also write it out as a conversion string here, and we just start with the 44.1 grams of propane. If you'll remember, this is just a recap of what we've done. We're multiplying that by the grams per mole of the propane. We're then multiplying by the mole-to-mole ratio between propane and oxygen. We are then multiplying by the last conversion factor, 32 grams of oxygen in 1 mole, and we're getting 160 grams of oxygen. And so that is the answer. Now, what if we would like to find the amount of product in a reaction when we've been given some amount of a reactant that we started with? It's very easy. It's the same process. We'll just take a different example here to make sure you understand. Find the mass of chlorine gas required to produce 5.00 times 10 to the negative third grams of chlorine monofluoride given an excess of fluorine gas. First, the chemical formula for that. And here is the balanced equation. Chlorine gas plus fluorine gas produces 2 moles of chlorine monofluoride. We know how much chlorine monofluoride we have in the problem. We have 5 times 10 to the negative third grams of that is produced. And we would like to know how much chlorine gas we had needed to start with. Here's the Here's the drawing, the pattern. First we convert to moles, then we take moles of chlorine monofluoride and find the moles of chlorine gas from the mole to mole ratio, and then lastly we convert into the number of grams of chlorine. So here are those steps. 5 times 10 to the negative third grams of chlorine monofluoride multiplied by the conversion factor. We know how many moles of chlorine monofluoride we have right here. Then will be to, again, use the mole to mole ratio to take us from the moles of chlorine monofluoride to the number of moles of chlorine gas. Here are the number of moles of chlorine monofluoride we just calculated. The ratio is 1 to 2, and here are the number of moles of chlorine gas that we get. Now we need to convert that number into the number of grams of chlorine. Here we multiply by 35.45 grams of chlorine per mole of chlorine, and we get this for the answer. Once again, if we write the conversion string out for this, these are just each of the steps we've done. We took what we knew initially, we multiplied by this conversion factor, we multiplied by the mole to mole ratio, and again multiplied by the conversion factor to get us to the number of grams of chlorine. So here is an opportunity for you to sort of practice this concept, and you can do it in 3 separate steps. You can do a conversion string, whichever way would work for you and whichever way you find easiest. Here's the problem. How many grams of xenon tetrafluoride are produced when 100 grams of fluorine are reacted with excess xenon? That means there's plenty of xenon to carry out this reaction. You don't have to worry about that, but if you'll pause your video right now and then turn it on, you can check your answers in the next slide. Here you can check your work. We have the reaction. I wrote that down one more time, and here is just the conversion string. You're welcome to do it in multiple steps if you want, but your answer should be 272 grams. Thank you guys, and we'll see you tomorrow.